In 1971, physicists loaded atomic clocks onto commercial airliners, flew them around the world, and returned to find that time had literally passed differently for the traveling clocks than for identical clocks that never left the ground. The experiment was called the Hafele-Keating Experiment, and it should have been impossible. Before these flights, the clocks were synchronized to an extraordinary degree of precision, ticking in perfect agreement, measuring the same second, the same nanosecond, the same fraction of a nanosecond. When the traveling clocks returned, they disagreed with the stationary clocks by precisely the amounts that Einstein's equations had predicted decades earlier. The difference was not a malfunction. It was not instrument drift or calibration error, or the vibrations of a commercial aircraft disturbing sensitive machinery. Time itself had passed at a different rate for the clocks that moved than for the clocks that stayed behind. This is the uncomfortable reality at the center of modern physics. Time is not fixed. It does not flow at the same rate everywhere in the universe, indifferent to motion and gravity and the conditions surrounding whatever is measuring it. Time warps. It stretches and compresses depending on how fast an object is moving and how deep it sits inside a gravitational field. The Hafele-Keating experiment did not discover this. Einstein had predicted it 60 years earlier, but it demonstrated something that pure mathematics could never fully communicate. It demonstrated that two identical objects, synchronized perfectly and then separated, could return having genuinely experienced different amounts of time. Not different measurements of the same time, different amounts of actual time. What makes this revelation so difficult to absorb is that the effect does not apply only to clocks. A clock is simply a device designed to make time's passage visible and countable. But every physical process is a clock. Every chemical reaction proceeds at a rate governed by time. Every biological process, cell division, heartbeat, the firing of neurons, the slow degradation of DNA, runs on the same universal timer that the atomic clocks were measuring. When physicists say that time passed differently for the traveling clocks, they are saying that every process aboard those aircraft aged at a different rate than every process on the ground. The pilots aged slightly differently than their families waiting at home. The difference was measured in nanoseconds across a single circumnavigation of the Earth, far too small for any biological system to detect. But it was real. It accumulated. It was measured. The traveling clocks lost 59 nanoseconds during the eastward journey and gained 273 nanoseconds during the westward journey, matching relativistic predictions to within the experimental uncertainty of the measurements. These numbers seem almost trivially small, but consider what they represent. Nanoseconds are not rounding errors in this context. They are direct evidence that the structure of time responded measurably to the motion of an aircraft flying at ordinary commercial speeds, not near the speed of light, not aboard some experimental rocket accelerating to relativistic velocities. On a commercial airliner carrying passengers and luggage, traveling at speeds humans had been moving at for decades. Time dilation was already happening at scales accessible to everyday technology. The Hafele-Keating experiment forced a confrontation with a question that most people never think to ask. We assume that time is something that exists outside of us, outside of matter, outside of the universe itself, a neutral backdrop against which events unfold at a single universal rate. This assumption feels so natural that it barely registers as an assumption at all. It feels like simple observation, and yet it is wrong. Time is woven into the fabric of space and matter. It responds to velocity and gravity the way that temperature responds to heat. Two clocks separated in space, moving at different speeds or sitting at different depths inside a gravitational field, are not measuring the same thing. They are measuring two genuinely different rates of time passing in two genuinely different regions of the universe. This is what the clocks revealed in 1971, and what every subsequent experiment has confirmed with increasing precision. The clocks were not broken, not drifting, not measuring incorrectly. They were faithfully recording two different versions of time passing in two different parts of the universe. Before Einstein, physicists assumed that if you measured the speed of light while running toward it, you would get a faster reading. The same way running toward a thrown ball makes it reach you sooner. This assumption seemed not just reasonable, but obvious, a natural extension of the Galilean relativity that had governed physics for 3 centuries. If a train moves at 60 kilometers per hour and a passenger walks forward through its cars at 5 kilometers per hour, an observer standing outside watches that passenger moving at 65 kilometers per hour. Velocities add together. They always had. Every experiment, every cannon fired, every stone dropped from a tower had confirmed this principle without exception. The universe appeared to operate on a simple, elegant arithmetic of motion that no serious physicist had reason to question. Then came the light experiments. In 1887, Albert Michelson and Edward Morley built an extraordinarily precise interferometer in Cleveland, designed to detect the difference in light speed depending on whether it was measured moving with or against Earth's orbital motion. The experiment assumed that light, like sound, travelled through a medium, a substance called the luminiferous ether, and that Earth's movement through this ether would produce measurable differences in how fast light appeared to travel in different directions. The results were catastrophic for the prevailing theory. No difference appeared. Light travelled at the same speed regardless of the direction measured, regardless of Earth's motion, regardless of the experimental conditions. The ether didn't exist, and velocity addition, the cornerstone of classical mechanics, appeared to simply stop working for light. Physicists spent nearly 2 decades constructing increasingly elaborate explanations for this result, each more convoluted than the last. Some proposed that the ether was dragged along by massive objects. Others suggested that measuring instruments physically contracted when moving through the ether, creating a false impression of constant speed. These attempts preserved the old framework by adding complications that could not themselves be directly tested. What none of them were willing to accept was the most direct interpretation of what Michelson and Morley had actually measured. Einstein accepted it. In 1905, he published the paper that didn't patch the old physics. It demolished it entirely. Einstein began with 2 postulates, stated simply enough to seem almost trivial. The first, the laws of physics are identical in all inertial reference frames, meaning that no experiment performed inside a uniformly moving laboratory can reveal whether that laboratory is moving or stationary. The second, the speed of light in a vacuum is constant at approximately 299,792 kilometers per second for all observers, regardless of the motion of the source or the observer. The first postulate was uncontroversial, a principle Galileo himself had understood. It was the second postulate that carried the full weight of what was coming. Consider what that second postulate actually demands. 2 observers are moving toward each other at half the speed of light. A beam of light passes between them. According to classical velocity addition, each observer should measure that beam moving at 1.5 times light speed relative to themselves. But Einstein's second postulate forbids this. Both observers must measure the same beam travelling at exactly 299,792 kilometers per second, no faster and no slower, despite their relative motion. This isn't a measurement error or an artifact of imprecise instruments. It is a fundamental feature of the universe that cannot be reconciled with classical mechanics without destroying something else. The question Einstein asked was, what exactly must be destroyed to make this work? The answer is simultaneity. The answer is absolute time. If the speed of light cannot change regardless of an observer's motion, then the only remaining variables are the measurements of distance and time themselves. For 2 observers in relative motion to measure the same light beam at the same speed, their measurements of time and space must differ. An observer moving relative to a light source must measure that source's clock as running slowly, and that source's distances as compressed along the direction of motion. Not appearing to run slowly due to signal delays or optical effects, actually running slowly. Time itself passing at a different rate, not as a perceptual trick but as a physical reality, written into the geometry of the universe. This was not a conclusion Einstein reached reluctantly. It was the only conclusion the mathematics permitted. Once the constancy of light speed was accepted as a genuine feature of reality, rather than an experimental anomaly to be explained away, the relativity of time followed with the iron logic of a mathematical proof. 2 clocks that are synchronized when they occupy the same point in space will disagree the moment they begin moving relative to each other, and their disagreement will grow in direct proportion to their relative velocity. There is no third option, no hidden mechanism that could restore absolute time while preserving the constancy of light speed. The universe simply does not permit both to coexist. Every experiment conducted since 1905, from atomic clocks on airplanes to particle accelerators to the GPS satellites overhead, has confirmed this conclusion with increasing precision and never once contradicted it. Time dilation is not a strange side effect of relativity. not a quirk or anomaly. It is the only logical consequence of a universe where light always travels at exactly the same speed for every observer, no matter what. The formula that describes time dilation is elegant in its simplicity and terrifying in its implications. At its core sits a single mathematical relationship known as the Lorentz Factor, a quantity that tells you precisely how dramatically time stretches depending on how fast an object moves through space. The equation itself requires no advanced mathematics to read. It states that the slowing of time depends on velocity divided by the speed of light, squared, subtracted from 1 under a square root. What that equation actually means, however, is something far stranger than its appearance suggests. Consider what happens at ordinary speeds. A commercial aircraft travels at roughly 900 kilometers per hour, which sounds fast until you compare it to the speed of light at approximately 1.08 billion kilometers per hour. At aircraft speeds, the velocity term in the Lorentz factor is so vanishingly small that the resulting time dilation amounts to nanoseconds across an entire flight. The effect is real, atomic clocks confirm it, but it falls far below anything a human being could perceive without instruments of extraordinary precision. At the speeds of everyday life, the formula quietly produces an answer of almost exactly 1, meaning time flows at almost exactly the same rate for a moving object as for a stationary observer. Almost. Not quite, but close enough that Newton's clockwork universe appeared to work perfectly for 3 centuries before anyone noticed the discrepancy. The numbers begin to shift meaningfully only as velocities climb toward a significant fraction of the speed of light. At 10% of light speed, roughly 108 million kilometers per hour, a velocity no human technology has approached, the Lorentz factor produces a time dilation of approximately 0.5%. For every 1,000 seconds experienced by a stationary observer, the moving object experiences about 995 seconds, measurable, significant, but not yet dramatic. A traveller moving at this speed for a year would return about 2 days younger than expected. The formula is working, but it has not yet revealed its full character. Push that velocity to 90% of the speed of light and the equation transforms into something genuinely difficult to absorb. At this speed, time for the moving object passes at roughly 44% the rate experienced by a stationary observer. For every year that passes on Earth, the traveller experiences only about 4.5 months. The Lorentz factor has climbed past 2, meaning a stationary observer watching a clock aboard this spacecraft would see it ticking at less than half normal speed. Every biological process aboard that ship, every heartbeat, every chemical reaction, every decay of every radioactive atom proceeds at less than half the rate it would if the ship were sitting still. This is not a distortion of perception. It is not an illusion produced by light travel delays. The time itself is different. At 99% of light speed, the factor climbs to approximately 7. A journey that takes 7 years, according to clocks on Earth, consumes only 1 year for the crew. At 99.9% of light speed, the factor exceeds 22. The universe, at this velocity, begins to compress in a way that makes journeys of enormous distance possible within a human lifetime, at an extraordinary cost that will be examined elsewhere. But the formula continues to accelerate beyond even this. At 99.99% of light speed, the Lorentz factor approaches 70. The gap between the traveller's experienced time and the time passing in the wider universe has grown so vast that the two clocks bear almost no relationship to each other. What the formula is approaching as velocity climbs toward the speed of light itself is a denominator of 0, a square root of 0. Division by 0 in the time equation means that time dilation approaches infinity, meaning that for an object actually moving at the speed of light, the elapsed time for that object would be 0. No time would pass at all. This is not a breakdown of the mathematics. It is the mathematics stating something precise and literal. At light speed, time stops. Photons, which travel at exactly c, do not experience time in any meaningful sense. From the photon's perspective, if such a perspective could exist, emission and absorption are simultaneous events with no duration between them. This is also why the speed of light functions as an absolute barrier for anything with mass. The Lorentz factor does not merely describe time dilation, it also governs the energy required to accelerate a massive object. As velocity increases, the effective inertia of the moving object increases as well, meaning that each additional increment of speed demands more energy than the last. At 90% of light speed, reaching 91% costs significantly more energy than reaching 90% did. At 99%, the next fraction of a percent costs more still. The curve climbs without limit. The energy required to push a massive object to exactly the speed of light is not large, not enormous, not astronomically large. It is mathematically infinite. No finite energy source, no matter how advanced, could ever supply it. An object with mass can get arbitrarily close to the speed of light, but each fraction of c closer requires exponentially more energy, meaning the universe has built an absolute speed limit directly into the structure of time itself. Imagine two twins, identical in every way, standing on a launch pad, and then one of them climbs into a spacecraft and leaves. The spacecraft accelerates to a significant fraction of the speed of light and departs toward a distant star, while the remaining twin watches it vanish from the sky and returns home to wait. Decades pass on Earth. The traveling twin eventually decelerates, circles the target star, and begins the long journey back. When the spacecraft finally lands and the hatch opens, the two siblings face each other, and one of them has aged 30 years while the other has aged perhaps 5. This is not a plot device borrowed from science fiction. This is a direct consequence of the equations described in the previous section, applied to two biological clocks moving through different reference frames at vastly different velocities. The scenario carries a name, the twin paradox. And the reason it is called a paradox has nothing to do with the result being wrong, because the result is entirely correct. The paradox lies in an apparent contradiction at the heart of the reasoning. Special relativity holds that motion is relative. There is no privileged stationary frame of reference in the universe. If the traveling twin is moving at high velocity relative to Earth, then from the traveling twin's perspective, it is equally valid to say that Earth is moving at high velocity away from the spacecraft. Both descriptions are legitimate within the framework of special relativity. But if each twin can legitimately describe the other as the one in motion, then each should observe the other's clock running slowly. And if each twin observes the other aging more slowly, how can they both arrive at the reunion with a definitive, measurable, agreed-upon age difference? It seems to generate a logical contradiction. If the paradox were real, the entire framework of relativity would collapse into incoherence. The resolution requires examining something that the symmetrical description quietly ignores. The two twins do not actually occupy equivalent situations throughout the journey. The stationary twin remains in a single inertial frame of reference from departure to reunion, experiencing no acceleration whatsoever. The traveling twin does not. To leave Earth, the spacecraft must accelerate. To reach the target star, it must decelerate. To return, it must accelerate again. To land, it must decelerate once more. Each of these transitions represents a change in the direction or magnitude of velocity, a change that only one twin experiences. The traveling twin switches between multiple inertial reference frames during the journey, and that switching is the source of the asymmetry. The situation is not symmetrical, and because it is not symmetrical, both twins agree on the same answer when they meet. The traveller is younger. The paradox dissolves entirely once the role of acceleration is properly accounted for. The scale of the age difference depends entirely on the velocity achieved. At 80% of the speed of light, the Lorentz factor produces a time dilation ratio of approximately 1.67, meaning that for every 10 years passing on Earth, the traveling twin experiences roughly 6. At 95% of the speed of light, the ratio climbs to approximately 3.2, compressing the traveller's experience of a 10-year Earth journey into something closer to 3 years of subjective time. Push the velocity to 99% of the speed of light, and a journey that spans decades on Earth might occupy only a few years for the person aboard the spacecraft. These are not approximations or theoretical idealizations. They follow directly from the formula introduced in the previous section, applied to real velocities producing real numbers. What makes this something other than a thought experiment is the evidence that exists outside any laboratory. Nature has already performed this experiment at scales far beyond anything human engineering has achieved, using particles called muons. Muons are elementary particles produced when high-energy cosmic rays strike atoms in Earth's upper atmosphere, roughly 15 kilometers above the surface. In their rest frame, muons are extraordinarily short-lived. Their average lifetime before decay is approximately 2.2 microseconds, a span of time so brief that even traveling at nearly the speed of light, classical physics predicts they should decay long before covering the distance between the upper atmosphere and the ground. The numbers are unambiguous on this point. At the speed of light, 2.2 microseconds allows for travel of roughly 660 meters, a small fraction of the 15 kilometers standing between their origin point and the surface. And yet muons arrive at the surface in substantial numbers. They reach sea-level detectors continuously in quantities that cannot be explained unless something is dramatically extending their effective lifetime from the perspective of the ground-based observer. That something is time dilation. The muons are traveling at approximately 99.9% of the speed of light, which produces a Lorentz factor near 22. From the ground's frame of reference, a muon's internal clock runs 22 times more slowly than a clock at rest, stretching its effective lifetime from 2.2 microseconds to nearly 50 microseconds, more than sufficient to complete the journey from the upper atmosphere to the surface. The travelling twins' clock runs slow for the same mathematical reason the muon's clock runs slow. The physics is identical. The scale differs. The principle does not. Muons created by cosmic ray collisions in the upper atmosphere survive long enough to reach the surface of Earth only because time is passing more slowly for them than for us. And we have measured this repeatedly with extraordinary precision. Speed is not the only thing that warps time. Everything covered so far, the twin who returns younger, the muons surviving their atmospheric descent, the atomic clocks that diverge aboard commercial flights, all of that follows from velocity alone, from special relativity and what happens when objects move relative to one another through space. But Einstein did not stop there. His general theory of relativity, published in 1915, revealed a second mechanism entirely, one that operates even when nothing is moving at all. Gravity itself warps time. The stronger the gravitational field surrounding a clock, the more slowly that clock ticks compared to a clock sitting in weaker gravity. This is not an extension of the velocity effect, not a variation on the same principle. It is a distinct phenomenon with its own origin and its own consequences, and it operates everywhere in the universe at every scale, continuously. To understand why gravity distorts time, it is necessary to understand what gravity actually is in Einstein's framework. Newton described gravity as a force acting at a distance between masses, an invisible pull that drew objects together across empty space. Einstein replaced this picture entirely. In general relativity, massive objects do not pull on each other through some mysterious force. Instead, they curve the fabric of space-time itself, and other objects simply follow the curved paths that result. What we experience as gravitational attraction is actually the geometry of space-time bending in the presence of mass. A planet doesn't pull a moon toward it. It creates a curvature in space-time through which the moon moves. This geometrical picture of gravity has a consequence that Newton's picture could never have predicted. If space-time itself is curved by mass, then time, being a dimension of space-time, is also distorted. A clock situated deep inside a gravitational well is not simply experiencing gravity. It is embedded in more severely curved space-time, and, as a result, time passes more slowly for it than for an identical clock positioned farther from the massive object. The practical implication is precise and counterintuitive. A clock sitting on the floor of a room ticks more slowly than a clock sitting on a shelf 1 meter above it, because the floor clock sits fractionally deeper inside Earth's gravitational field. A clock at sea level accumulates time more slowly than a clock positioned on a mountaintop, thousands of meters higher. The difference at these scales is extraordinarily small, far too small for any ordinary timepiece to reveal, but it is real, it is measurable, and it follows Einstein's equations with exact fidelity. The higher the altitude, the weaker the gravitational field, and the faster time flows. Descend toward a gravitational source, and time slows. The pattern is consistent and universal, operating regardless of the composition of the clock or the physical process being measured. Biological processes, radioactive decay, atomic oscillations, all of them slow in stronger gravitational fields because time itself is the thing that is changing. The first direct experimental confirmation of gravitational time dilation came in 1959 from a deceptively simple experiment conducted inside a building at Harvard University. Physicists Robert Pound and Glenn Rebka measured how the frequency of light changed as it traveled vertically upward through a height difference of approximately 22 meters. According to general relativity, light emitted deep in a gravitational field should lose energy climbing out of that field, shifting to a lower frequency, a phenomenon called gravitational redshift. Pound and Rebka measured exactly this shift, with results falling within 10% of what Einstein's equations predicted. 5 years later, a refined version of the same experiment achieved results within 1% of the predicted value. This was the first time that gravitational time dilation had been confirmed through direct measurement, and it validated not just a prediction but an entirely new way of understanding what gravity is and what time is. The gravitational redshift observed in that experiment is the spectral signature of time passing at different rates at different heights, rendered visible in the frequency of light. The consequences of this effect accumulate in ways that become remarkable over long timescales. Consider what it means for Earth itself. The planet formed approximately 4.5 billion years ago from the same collapsing cloud of material, with its core and its surface originating simultaneously. Since then, the core has sat deep inside Earth's gravitational field, subjected to far greater gravitational potential than the crust surrounding it. According to general relativity, time has been passing more slowly at the core than at the surface for the entire 4.5 billion years of Earth's existence. The difference in the rate of time at any given moment is vanishingly small, a fraction of a second per year. But multiplied across billions of years, that tiny disparity accumulates to a measurable quantity. Richard Feynman identified this consequence, and subsequent calculations confirmed it. Earth's core has experienced approximately 2.5 fewer years of elapsed time than its surface, despite the two having formed together and never separated. The surface of the planet has simply aged faster, sitting in weaker gravity, with time flowing at a slightly higher rate for every second of the planet's existence. This is the nature of gravitational time dilation at the scales available to us on Earth. Effects so small that only the most sophisticated instruments reveal them, yet effects that are entirely real and that accumulate relentlessly. Move to more extreme gravitational environments, and the consequences become far more dramatic. But the principle is the same one confirmed in a Harvard building in 1959 by two physicists measuring a beam of light crossing 22 meters of ordinary air. The core of the Earth, sitting deeper inside a gravitational well than the crust above it, is measurably younger, by about 2.5 years, despite forming at exactly the same moment as the rest of the planet. Every time someone uses GPS navigation, they are relying on corrections that would make no sense without Einstein. The global positioning system consists of roughly 30 satellites orbiting Earth at an altitude of approximately 20,000 kilometers, each carrying onboard atomic clocks of extraordinary precision, each transmitting timing signals that receivers on the ground use to triangulate position. The system works because those clocks stay synchronized with clocks on the ground to within nanoseconds. But here is the uncomfortable reality buried inside that engineering. Left uncorrected, the clocks on those satellites would drift so dramatically out of sync that the entire system would become useless within hours. Two separate relativistic effects act on every GPS satellite simultaneously, and they push in opposite directions. The first comes from the satellite's orbital velocity. Moving at roughly 14,000 kilometers per hour, the satellites experience special relativistic time dilation of the kind described by Einstein's 1905 equations. The same effect that causes muons to survive long enough to reach the surface of Earth. The same effect that ages the traveling twin more slowly than the twin left behind. Velocity slows time. For the GPS satellites, this effect causes their onboard clocks to lose approximately 7 microseconds every single day, relative to clocks sitting on the ground. The second effect comes from gravity, and it runs in the opposite direction. At 20,000 kilometers of altitude, Earth's gravitational field is considerably weaker than at the surface. As general relativity predicts, clocks in weaker gravitational fields run faster. The satellites sit higher in the gravitational well, further from Earth's mass, and time flows more quickly for them as a result. This gravitational time dilation causes GPS satellite clocks to gain approximately 45 microseconds per day, relative to ground clocks. These two effects do not cancel. They combine into a net gain because the gravitational acceleration far outweighs the velocity-based deceleration at these particular orbital parameters. Subtract the 7 microseconds lost to velocity from the 45 microseconds gained from reduced gravity, and the satellite clocks end up running fast by a net total of 38 microseconds every day. 38 microseconds sounds trivially small. It is not. The speed of light is approximately 300 million meters per second. In 38 microseconds, light travels roughly 11 kilometers. GPS receivers determine position by measuring the travel time of signals moving at the speed of light, so a 38 microsecond timing error translates directly into a positional error of approximately 11 kilometers, accumulating every single day, compounding without bound. An 11-kilometer error per day would render GPS navigation not merely inaccurate but catastrophically wrong. Aircraft approaches, maritime navigation, military targeting systems, autonomous vehicles, emergency response coordinates – none of these could function with errors of that magnitude building continuously. The system would be worse than useless. It would be dangerous because it would report positions with apparent confidence while being profoundly wrong. The engineers who built GPS understood this. They had to. Designing the system without accounting for relativistic time dilation would have been equivalent to designing a bridge while ignoring the effects of gravity. The solution they implemented is remarkable in its elegance, and it is also deeply strange when considered carefully. Before launch, each satellite's clock is deliberately set to run at a slightly incorrect frequency. The onboard oscillators are adjusted to tick at 10.2299999543 MHz instead of the standard 10.23 MHz. This pre-compensated rate is specifically calculated so that when the satellite reaches orbit and both relativistic effects begin operating simultaneously, the net result is a clock running at exactly the right rate as observed from the ground. The satellite's clock is wrong in a way precisely engineered to become right. This is not a software correction applied after the fact. It is not a ground-based adjustment transmitted to the satellites periodically. The compensation is baked into the hardware before the satellite ever leaves the launch pad, calculated using equations that Einstein derived over a century ago. The satellite ascends, reaches its orbital altitude, begins its relativistic journey through a weaker gravitational field at high velocity, and the two effects converge on the pre-calculated correction. What had been a deliberately mistaken clock becomes, in orbit, a synchronized one. Consider what this means beyond the technical details. The global positioning system is not simply influenced by relativistic physics in some marginal academic sense. Relativistic physics is load-bearing infrastructure inside the system. Remove Einstein's corrections and the system fails on day one. The fact that billions of people use GPS every day without thinking about special relativity, without thinking about general relativity, without thinking about Albert Einstein at all, does not change the fact that both theories are silently operating inside every position fix, every turn-by-turn direction, every geotagged photograph. The physics is not optional, it is not approximate, it is exact, and the engineering reflects that exactness down to the 11-digit precision of the adjusted oscillator frequency. Relativity is often described as a theory of the very large and the very fast, relevant to black holes and particle accelerators and hypothetical spacecraft, but disconnected from ordinary life. GPS dismantles that description completely. The satellites that make modern navigation possible are orbiting at speeds and altitudes where the predictions of special and general relativity diverge measurably from Newtonian physics, and the engineers who built the system had no choice but to take those predictions seriously. The satellites overhead, quietly ticking at precisely the wrong rate so that they read the right rate from the ground, are monuments to the fact that time dilation is not a theory. It is engineering. In 2010, physicists at the National Institute of Standards and Technology built clocks precise enough to detect time dilation at speeds a car could reach on a highway. These were not experimental prototypes operating under exotic laboratory conditions, not instruments cooled to near absolute zero or shielded behind layers of electromagnetic isolation. These were atomic clocks, the most precise timekeeping instruments humanity has ever constructed, and they revealed something that challenges every intuition we carry about the ordinary world. At 25 miles per hour, time runs measurably slower. At a height difference of just 1 foot above the ground, time runs measurably faster. The effect is real, the measurements are confirmed, and the universe does not care whether the numbers seem too small to matter. The 2010 experiment placed two of these extraordinary clocks at slightly different heights, separated by no more than the distance between a floor and a ceiling in a modest room, and measured the difference in their tick rates. The clock positioned 1 foot higher accumulated time faster than the clock positioned 1 foot lower, exactly as general relativity predicts. This is not a rounding error accumulated over geological timescales. This is a measurable difference in the rate of time passing in two locations that a person could span with an outstretched arm. The person living in an upstairs apartment is aging faster than the person living directly below them in the basement. Not metaphorically, not approximately, not in some abstract relativistic sense that only matters near black holes or neutron stars. Literally, physically, measurably faster, because time itself runs at different rates depending on how deep inside a gravitational field a given clock happens to sit. The same experiment demonstrated velocity-based time dilation at speeds that any automobile on any highway could achieve. Moving a clock at 25 miles per hour slowed its tick rate relative to an identical stationary clock. The difference is fantastically small, accumulating to only a few nanoseconds over the course of a lifetime of driving, but the difference is there, and it is real. Every person who has ever driven a car has aged fractionally less during that journey than they would have if they had remained motionless. Every commercial airline passenger who has flown from one continent to another has landed measurably younger than their counterpart who stayed home, though the difference amounts to something on the order of tens of nanoseconds per flight. These numbers sound trivial. They are not trivial. They represent time dilation operating continuously, at human scales, in the environment that surrounds every living person on this planet. What makes these small-scale conformations particularly significant is that they eliminate any remaining possibility that time dilation is a phenomenon exclusive to extreme environments. The Hafele-Keating Experiment of 1971 demonstrated the effect using commercial airliners. The 2010 NIST experiment brought that demonstration down further still, to speeds and distances within the range of everyday human experience. The physics does not switch on at some threshold velocity or activate only when gravity becomes sufficiently intense. It operates at every speed, at every altitude, in every moment. The difference between the tick rate of a clock on the floor of a building and a clock on the roof is accumulating right now in every building on Earth in a continuous drift that never pauses and never reverses. Consider what this means extended across a longer time frame and a greater distance. Voyager 1 was launched in 1977 and has been traveling through space at speeds that dwarf anything a human being has ever directly experienced. As it accelerated away from the gravitational influence of the Sun and the planets, two competing effects began acting on the clocks it carries. Its velocity caused special relativistic time dilation, slowing its elapsed time relative to Earth. Its increasing distance from the Sun's gravitational field removed it from the gravitational time dilation that all instruments on or near Earth experience continuously. These effects partially offset each other, but the net result is that Voyager 1 has aged differently than it would have if it had remained stationary relative to Earth. This is not a dramatic difference in human terms. It does not represent decades of separation or civilizational change, but it represents something perhaps more unsettling in its quietness: the accumulated time dilation of an object simply moving through space and climbing out of a gravitational well over half a century of continuous travel. The spacecraft and the Earth have been drifting apart not only in distance but in time, tick by tick, since the day of launch. Voyager 1, launched in 1977 and now billions of miles from Earth, is approximately 1.25 seconds younger than it would be if it had simply sat in a parking lot for 50 years. If gravitational time dilation becomes stronger closer to massive objects, then the most extreme gravitational environment in the known universe, the event horizon of a black hole, represents something close to the complete stopping of time. What happens at that boundary challenges every intuition we carry about how time is supposed to behave, and the mathematics produces conclusions that should be impossible, yet remain entirely consistent with general relativity's equations. A black hole forms when a sufficiently massive object collapses under its own gravity to a point of essentially infinite density. The gravitational field surrounding this singularity grows more intense with proximity, following a curve that does not plateau or level off but climbs toward a value that the equations can only describe as approaching infinity at the event horizon itself. The event horizon is not a physical surface, not a wall or membrane, but simply the boundary beyond which the escape velocity exceeds the speed of light. Nothing that crosses that threshold can return, and at that threshold, gravitational time dilation reaches its absolute extreme. Consider an observer watching a distant spacecraft fall toward a black hole's event horizon. From that distant vantage point, what they witness is one of the most disorienting predictions in all of physics. As the spacecraft descends through progressively stronger gravitational fields, its clock appears to run more and more slowly relative to clocks far from the black hole. The spacecraft's movements slow. Radio signals transmitted from the descending craft arrive at increasingly stretched intervals, their frequencies shifted toward the red end of the spectrum as time dilation and gravitational redshift compound each other. It appears to slow, dim, and freeze at that boundary, its final moments stretched across an effectively infinite span of time as seen from outside. A distant observer would never actually witness the crossing. The spacecraft simply fades, suspended at the threshold, becoming dimmer and more redshifted until it disappears from detection entirely. The astronaut aboard that spacecraft experiences something completely different. From their perspective, nothing dramatic marks the crossing of the event horizon. There is no wall, no flash of light, no physical sensation that announces the transition. Their instruments continue functioning normally. Their heartbeat continues at its ordinary pace. Time, as they experience it, passes without interruption. The event horizon is invisible to them, a mathematical boundary that their local physics cannot detect in any direct way. Only later, deeper inside the black hole, would the gravitational tidal forces become strong enough to produce effects they could measure. But at the moment of crossing, time dilation is something that exists only in the reference frame of observers watching from outside, not in the reference frame of the person falling through. This asymmetry between reference frames is precisely what general relativity predicts. Neither observer is wrong. The distant observer genuinely sees time freeze at the event horizon. The infalling astronaut genuinely experiences no such freezing. Both descriptions are equally valid, each correct within its own reference frame, and the two accounts can never be compared directly because no information can travel outward from beyond the event horizon to reconcile them. Neutron stars offer a less extreme but equally measurable version of this same phenomenon. A neutron star is the compressed remnant of a massive star that has undergone a supernova explosion, packing roughly twice the mass of the Sun into a sphere approximately 20 kilometers across. The gravitational field at a neutron star's surface is roughly 200 billion times stronger than Earth's surface gravity. Clocks at the surface of a neutron star run measurably slower than clocks at a safe distance, with the time dilation effect reaching several tens of % depending on the star's exact mass and radius. A clock sitting on the surface of a typical neutron star would accumulate noticeably less time than an identical clock orbiting far above it, and the difference would be detectable within hours. Neutron stars therefore represent gravitational time dilation operating at scales far beyond anything achievable in laboratory conditions, yet still short of the extreme environment near a black hole's event horizon. The practical implications extend beyond thought experiments. A spacecraft that descended close to a stellar mass black hole, not crossing the event horizon but orbiting at a distance where gravitational time dilation is substantial, would experience time at a dramatically reduced rate relative to clocks far from the black hole. The crew aboard such a spacecraft might experience weeks or months of elapsed time, while years or decades accumulated in the universe around them. The film Interstellar depicted exactly this scenario when characters descend toward a massive black hole and return to find that decades have passed for the crew member who waited at a distance. The film dramatized certain aspects for narrative effect, but the underlying gravitational time dilation physics is accurate. In its fundamentals, a sufficiently strong gravitational field maintained over a sufficient duration produces real and irreversible age differences between observers in different locations. This creates an uncomfortable possibility that general relativity simply does not prohibit. A traveler who spent years near a sufficiently massive object would return to a universe that had aged far beyond their own biological clock. The stars would have shifted positions, civilizations would have risen and fallen, the people they had known would be long dead, the traveler would not have cheated time or bypassed it. They would simply have experienced less of it, moving more slowly through the time dimension because the geometry of spacetime near massive objects forces exactly that result. Spend enough time near a sufficiently massive object and you could return to a future millions of years ahead, not through suspended animation or science fiction machinery, but simply because time itself moves slower where you were. The universe is approximately 93 billion light-years across in observable terms, and the nearest star system beyond our own sights over 4 light-years away, distances that seem to make interstellar travel a fantasy. Alpha Centauri, the closest stellar neighbour to our Sun, requires more than 4 years to reach, even if a spacecraft could somehow travel at the speed of light itself. The next significant candidates for habitable worlds lie tens, hundreds, or thousands of light-years distant. By any conventional measure of human endurance and engineering, these distances represent an absolute barrier to exploration. But the physics examined in preceding sections introduces a factor that classical thinking never accounted for, a factor that transforms the mathematics of interstellar distances in ways that border on the extraordinary. Time dilation does not shorten the physical distance between stars. What it does is compress the subjective experience of crossing that distance, sometimes dramatically, sometimes to a degree that challenges intuition about what travel even means. Consider a spacecraft accelerating to 95% of the speed of light and maintaining that velocity toward a star system approximately 10 light-years away. From the perspective of observers remaining on Earth, that journey takes slightly more than 10 years in each direction, meaning the round trip consumes just over 2 decades of Earth time. But the Lorentz factor at 95% of light speed sits near 3.2, meaning that for every 3.2 years elapsed on Earth, approximately 1 year passes aboard the spacecraft. The crew experiences a one-way journey of roughly 3 years. The round trip, by their subjective experience, consumes only about 6 years of their lives. A traveller who departed Earth at the age of 25 would return biologically at approximately 31, while more than 20 years had passed on the planet they left behind. Their contemporaries would be approaching 50. The asymmetry is not a paradox, not a mathematical trick, not a flaw in the calculation. It is what the equations demand, and it is what experiment has confirmed repeatedly through particles and clocks and atomic precision measurements. At 99% of the speed of light, the Lorentz factor climbs to approximately 7. The same 10 light-year journey that consumed 3 subjective years at 95% of light speed now compresses to less than 18 months of experience time for the crew, while Earth ages by more than 10 years. Increase velocity further to 99.9% of light speed, and the Lorentz factor approaches 22. That 10 light-year crossing shrinks to roughly 5 months of subjective crew time, while more than a decade passes at the origin point. The universe, measured by human lifespans rather than light travel times, begins to collapse inward. Destinations that appear impossibly remote when measured by the distance light requires to cross them become reachable within a career, within a generation, within a human life. Did the spacecraft achieve sufficient velocity? The galaxy contains approximately 100 billion stars distributed across a disk, roughly 100,000 light-years in diameter. At 99.9% of the speed of light, a traveller could cross that entire structure within a subjective lifetime, while roughly 100,000 years elapsed on Earth. This is where the physics stops being merely technical and begins to carry consequences that deserve careful examination. The compression of subjective travel time does not pause or soften the passage of time elsewhere. Every year a relativistic traveller saves through time dilation is a year that continues to accumulate normally for every person, every institution, every civilization they left behind. A mission departing Earth in the present decade and travelling at 95% of light speed to a star 40 light-years distant would return by crew reckoning in approximately 25 years. Earth reckoning would place the return date more than 80 years after departure. The traveller steps off a spacecraft onto a planet where everyone who knew them personally is either elderly or dead. the eye, institutions that funded the mission may no longer exist in recognizable form. The languages spoken may have drifted, the technology will be unrecognizable. The traveler aged 25 years, the civilization aged 80. That gap cannot be recovered or negotiated. It is written permanently into the physical record of the universe by the same equations that make GPS satellites require pre-launch clock corrections and muons survive their journey through the atmosphere. The implications compound at greater distances. A mission to the galactic core, roughly 26,000 light-years distant, could be completed within a human lifetime at sufficiently high relativistic velocities, while 26 millennia pass on Earth. The traveler would return biologically middle-aged to a civilization separated from their departure point by a span of time longer than recorded human history. There is no communication that bridges this asymmetry while it accumulates. Signals sent from the spacecraft travel at light speed and arrive years or decades after transmission. Replies arrive years or decades after that. The connection between traveler and origin world degrades with every additional fraction of light speed the spacecraft achieves, not merely through distance, but through the divergence of experience time. What this means practically is that relativistic interstellar travel, if it ever becomes achievable, does not solve the isolation problem of deep space travel. It transforms it into something more permanent and more total. The traveler does not endure a long journey and return to a world they recognize. They purchase compressed travel time with an irreversible departure from the timeline of every person and place they knew. The distances become survivable. The separation does not. Time dilation turns interstellar travel from a question of whether the distances are possible into a question of whether you are willing to leave everything you know behind forever. Newtonian physics assumed that time was a river flowing at the same rate for everything in the universe, indifferent to motion, indifferent to gravity, indifferent to the conditions of the observer. And it was completely wrong. For more than 2 centuries, this picture was so deeply embedded in physics that it went largely unquestioned. Time was time. A second meant the same thing on Earth as it did on the far side of the galaxy. And Isaac Newton himself wrote that absolute time flows uniformly without regard to anything external. Every equation in classical mechanics depended on this assumption, and every one of those equations gave the wrong answer whenever the objects involved moved fast enough or sat deep enough in a gravitational well to expose the error. What Einstein recognized and what the evidence from atomic clocks, muon lifetimes and GPS satellites has since confirmed beyond any reasonable dispute is that time doesn't exist independently of the physical universe. It cannot be separated from space, from gravity, or from motion. It is a dimension woven together with the 3 dimensions of space into a single 4-dimensional structure, and that structure deforms. It curves under the influence of mass. It compresses and stretches under the influence of velocity. The rate at which time passes at any given location is not a fixed property of the universe, but a local condition that depends entirely on circumstances. The framework that replaced Newton's picture is called spacetime, and it demands a fundamentally different way of thinking about motion. In spacetime, every object is always moving, even objects that appear perfectly stationary. An object at rest in space is moving entirely through the time dimension, advancing through time at the maximum possible rate. An object moving through space is diverting some of that motion away from the time dimension and into the spatial dimensions instead. The combined rate of movement through both space and time always equals c, the speed of light. This is not a metaphor or a simplification. It is the actual geometric relationship that governs how time dilation works. This produces a counterintuitive consequence that sits at the heart of everything covered in this series. The faster an object moves through space, the slower it moves through time, because the total motion through space-time is fixed. An object traveling at 90% of the speed of light is devoting the vast majority of its space-time motion to spatial movement, leaving very little remaining for temporal movement. Its clock runs slowly not because of any mechanical effect or physical interference with the clock's components, but because the object is genuinely moving through time more slowly. Time dilation is not something that happens to clocks. It is what time itself does under those conditions. This framing resolves the question of why nothing with mass can ever reach the speed of light. At that velocity, the entirety of an object's space-time motion would be consumed by spatial movement. Nothing would remain for movement through time. Time would effectively stop for that object, which creates a cascade of physical impossibilities. Mass cannot exist in a state where time has stopped. The energy required to accelerate a massive object to light speed approaches infinity as velocity approaches c, and this is not an engineering limitation or a practical obstacle. It is the universe enforcing a geometric constraint built into the structure of spacetime itself. What this means for the concepts of past, present, and future is deeply unsettling. In Newtonian physics, the present moment is universal. Every object in the universe shares the same now, and the sequence of past, present, and future applies identically everywhere. Special relativity demolishes this picture entirely. Two observers moving at different velocities relative to each other will disagree about whether two spatially separated events are simultaneous. An event that observer A measures as happening at the same moment as another event will, according to observer B moving at a different velocity, happen at a measurably different time. Neither observer is wrong. Both measurements are correct within their own reference frames, and there is no third frame with special authority to declare which is the true sequence of events. This relativity of simultaneity means that the present moment is not a universal property of the universe. It is a local one. Each observer has their own present, their own slice through spacetime that they call now, and that slice is tilted at a different angle through spacetime depending on their velocity. Two observers moving at high velocity relative to each other might disagree not just about the timing of events, but about their order. For events separated by large enough distances and small enough time intervals, observer A might measure event X happening before event Y, while observer B measures Y happening before X. This is not a paradox or a contradiction. It is simply what spacetime geometry requires. Physicists describe this by saying that there is no privileged reference frame, no special location or state of motion from which the true sequence of events can be read. The universe does not carry a master clock. It carries an infinite collection of local clocks, each running at its own rate, each equally valid, none more correct than any other. The experience of time as a flowing, universal, shared dimension is a feature of human perception built from life at slow speeds and weak gravitational fields. Expand the range of conditions, and that familiar river dissolves into something far stranger and more fragmented. There is no universal present, no cosmic clock ticking at the same rate for all observers, no shared moment called now that connects all things. Only an infinite collection of reference frames, each aging through time at its own rate, each equally correct. Every region of the universe is aging at a slightly different rate. This is not a minor technical footnote to the physics we have been examining. It is a fundamental feature of the cosmos that makes the very concept of a universal age deeply problematic. The same mechanisms that cause an atomic clock on an airplane to drift away from an identical clock on the ground are operating at every scale across billions of light years, producing a universe where different regions have genuinely experienced different amounts of elapsed time since the Big Bang. Consider what sits at the centers of most large galaxies. Supermassive black holes, some containing the mass of billions of suns, generate gravitational fields of extraordinary intensity in their surrounding regions. Matter orbiting close to these objects, the accretion disks and gas clouds pulled into tight orbits at substantial fractions of the speed of light, is subject to both gravitational and velocity-based time dilation simultaneously. Time near the center of a galaxy like M87, which harbors a black hole weighing approximately 6.5 billion solar masses, is passing measurably more slowly than time in the sparse regions between galaxy clusters where gravitational fields approach zero. These two environments, separated by tens of millions of light years, have been aging at different rates since they formed. The matter near that black hole has experienced less elapsed time than equivalent matter drifting through an intergalactic void, despite both existing for what we loosely call the same cosmic epoch. The expansion of the universe introduces a related distortion that operates differently but produces mathematically parallel effects. When astronomers observe a galaxy 10 billion light-years away, the light reaching their instruments was emitted 10 billion years ago. But the expansion of space during those 10 billion years of transit has stretched that light, shifting it toward longer wavelengths, a phenomenon called cosmological redshift. This stretching of light is not identical to relativistic time dilation, but the mathematics describing it bears a striking resemblance to the Lorentz Factor. and the two effects produce similar observational signatures. The farther a galaxy sits, the more dramatically the expansion of space has stretched the light it emits, and the more distorted our view of its time becomes. We are not simply looking into the past when we observe distant galaxies. We are looking into a past whose time was itself flowing at a different rate relative to our own, stretched and modified by expansion over billions of years of travel. This creates an uncomfortable possibility for anyone attempting to assign the universe a single, definitive age. The standard figure of approximately 13.8 billion years represents a carefully calculated estimate derived from measurements made in our specific region of spacetime using our specific reference frame. But a civilization orbiting close to a supermassive black hole for its entire history would calculate a substantially different elapsed time since the Big Bang. And by the logic of relativity, their calculation would not be wrong. Their clocks would have genuinely ticked fewer times. Their atoms would have genuinely undergone fewer oscillations. They would have experienced less time in every physical sense that the word experience can carry. Deep intergalactic voids, the enormous near-empty regions between galaxy filaments stretching hundreds of millions of light-years across, represent the opposite extreme. With minimal mass nearby and no significant gravitational wells, time in these regions flows closer to the maximum possible rate. Matter in a void has been aging faster in the relativistic sense than matter clustered around the massive structures that dominate the observable universe's large-scale architecture. The universe's own structure, the cosmic web of filaments and voids that emerged from the density fluctuations of the early universe, has sorted matter into regions aging at systematically different rates. What this means is that the observable universe contains no single moment that can be called now, no unified present that connects all locations simultaneously, and no single elapsed time that describes how old everything is. The tools that let engineers correct GPS satellites and physicists track muon decay are the same tools revealing that the universe's history is not a single story told at one pace. The universe does not have one age. It has as many ages as it has reference frames, each one a slightly different answer to the question of how much time has passed since everything began.